and welcome to the Chicago Council on Science and Technology's Body and Machine Epidermal Electronics program. Welcome to all in attendance and those joining us via live stream. And I'd also like to extend a special welcome to the high school students from Chicago Tech Academy. Are there any other high school students as well? There are a couple of other schools who are supposed to be here as well. Any others? No? I'm Mitra Datta. I'm the Vice Chancellor for Research at University of Illinois at Chicago, and I'm a member of the Board of Directors for the Chicago Council of Science and Technology. For those who are unfamiliar with us, the Chicago Council on Science and Technology is a not-for-profit, membership-based organization that brings together universities, national labs, museums, and industry, and we pull research and researchers out of their labs and bring them directly to you. We focus on the Chicagoland area, where we are very rich in science and technology, and we showcase the importance of this work in our region and our community. So today is the 86th such program that C2S2 has produced in the past 7 years, and we could not have made it this far without our wonderful members, partners, sponsors, and advocates. If you like what you hear tonight, I encourage you to join C2ST, and if you join, you will get into most of our programs for free or at discounted rates. So it is my privilege and honor to introduce Dr. John Rogers, professor at our sister campus, University of Illinois at Urbana, Champaign, who has a primary appointment in the Department of Materials Science and Engineering, and also director of the Site's Materials Research Lab. If I spend time talking about all his credentials, we'll be here all evening, so I want to quickly move on to just some highlights and mention that his work is in fundamental and applied aspects of materials and patterning techniques for unusual electronic and photonic devices, with an emphasis on biointegrated and bio-inspired systems. He has published nearly 400 papers and has invented 80 patents, of which 50 are licensed or in active use. His research has been recognized by many awards, including a MacArthur Genius Fellowship, Amundsen MIT Prize in 2011, and he was also one of the Bill and Melinda Gates Foundation Grand Challenge Exploration winners. In addition to all of this, John is a fantastic speaker, and we have a great treat ahead of us. So I'll just sit down and turn this over to John.
Okay. All right, well, thanks very much for that introduction. I prefer to keep expectations low, however, but it's maybe a little bit too late for that. But it's good to be here and have a chance to talk to you guys about some of the things that we've been thinking about in my group at University of Illinois. As was mentioned, I'm a material scientist. That's the department where I have my primary appointment. And within material science and engineering, I'm particularly interested in electronic materials and the sorts of things that new ideas in electronic materials could offer in terms of new classes of electronic technologies. And that's what I'll talk to you about today. One particular topic that we've been working on the last 7-8 years or so, we refer to it as epidermal electronics, in the sense that, unlike conventional electronic devices that are built on the surfaces of silicon wafers, these are technologies that are constructed to have physical properties that match the epidermis. So the same kind of mechanical modulus, the bendability, the capacity to stretch, same thickness, areal mass density, same thermal properties. So it really melts right into the surfaces and the textures of the skin in a way that's almost invisible to the person wearing the device. And I'll step you through a number of different things that we think are valuable that arise from that capability. But for now, you can consider it really as an advanced wearable electronics technology, kind of going beyond what's out there today. And so that'll, really serve as a starting point for what I want to tell you about. And, to give you a sense of what we're doing, it's useful to provide a historical perspective on wearables, where it started, where it is today, and where it's going in the future. So, wearable electronics is kind of hot these days. It's not a new idea. If you look back, in the late 40s and early 50s, you could see that people were already thinking about it in those days. I mean, pretty clunky hardware. This actually predates the invention of the transistor. And so, this guy has this type of stylish hat that forms the antenna, and he has some nickel-cadmium cells down here and a radio and wires running around. And I think the idea was entertainment, though it's hard to see how that would really work in a realistic way. But anyway, people have been thinking about wearables. Like I said, this is back from the vacuum tube days, and so that example was by no means unique. So you had pretty clunky hardware, so you had to get creative about how to use it. So it becomes sort of a fashion statement. The vacuum tubes themselves, some kind of horns on this hat, and you got an antenna back here. So it's interesting. People have been contemplating it for a long time. I mean, these are sort of wearable radios. You can see the headphones here, and as once the transistor was invented, then the radios could be much smaller. You had Walkmans, and later iPods and so on. Really, though, still geared for entertainment purposes. Sound systems essentially is what those devices were designed and built to do. But what has really happened, beyond the invention of the transistor, is really a relentless miniaturization of the transistor dimension. Which allows you to pack a lot more computing power into ever smaller sizes. And the consequence of that, I think, in the context of wearables, is you move from a mode of use that's centered around entertainment to things that are nowadays built to integrate with your body, for a purpose, in the sense of measuring activity, for example. And so I have one of these on it. You've seen that, these are Fitbit devices. The Jawbone has something similar to this. It sort of, integrates with the body in kind of a loose way, very much like a watch. So there isn't an intimate interface between the electronics and the body, but at least you can start measuring parameters. Accelerometry is essentially what's done these days to assess fitness. And that's a pretty primitive measure of physiological status and activity. It's accelerometry. So I think what you see is moving from this to things like this that press more intimately against the skin, and then kind of use the skin as a window into internal body processes, so you can get more information than just accelerometry. And at this point, the device limitations begin to be apparent. Although the systems are much smaller than they used to be in these days, they're still rigid, hard, clunky things, right, that work in a wristwatch format, but in this kind of geometry become a lot less appealing, because you have a hard piece of electronics sort of pushing up against your body, and that becomes highly irritating and uncomfortable over time. So you might ask, where are things going in the future? And one future would be pretty obvious. It's just an extrapolation of going from here to here, in the sense of this miniaturization, this Moore's law scaling in electronic technology. So things will get very much smaller, they'll get faster, more powerful, and by the way, they also get cheaper over time. But if you don't have a roadmap for getting this electronics intimately interfaced with the skin, it's open to question whether you're going to be able to move beyond this kind of coarse wellness and fitness functionality to something more meaningful. And so that's been the emphasis of our research, is to try to go from the kind of boxy, rigid electronics that exist today and focus not on their size miniaturization, but on morphing their physical properties to look more like biology. So things that, instead of being planar and rigid and brittle, are soft, curvilinear, textured, and able to laminate onto important organs of the body. I'll tell you about skin integration, but I will mention that the same ideas apply to other organs, internal organs in the body. We've done a lot of work on brain-integrated devices and devices that, that wrap the surface of the heart. But this is a different type of future than the one I just articulated, and our hope is that it leads to a qualitative advancement in the way that the devices can function. Really advanced healthcare diagnostics, clinical quality data on sort of a real-time, everyday basis, and not only measurement, but also stimulation and therapy and so on. So that's kind of the context, the direction that the mainstream efforts in electronics are moving into the future, and our spin on things and where we'd like to try to make a contribution. So why can't you do that today? Why can't you make a piece of electronics that interfaces with the skin in this kind of epidermal or skin-like format? And it really has to do with the fact that every integrated circuit that's ever been built from the very earliest days of the technology have been constructed on these pieces of material. These are the substrates on which you etch integrated circuits. They're basically plates of glass. I mean, this, in terms of their mechanics, I mean, this is silicon. These are discs. They're maybe a millimeter in thickness, but they have the rigidity of glass. They have the same kind of mechanical fragility as well. And it turns out, this is a great platform for doing electronics, and it served the industry extremely well. It's fine if you want to build a laptop or a cell phone, you put something in your pocket. It doesn't need to necessarily stretch or adapt to curved surfaces. But this platform is a constraint. If you want to get things integrated with the skin, which clearly has much different mechanical properties and geometries than that wafer. So that really is the essential challenge. And the way that people do integrate electronics with the skin involve approaches like those that I showed you a couple slides back, or if you go to the hospital, you're familiar with these kinds of devices. Basically, point contact electrodes that paste onto the skin with a little bit of conductive coupling gel, and then from that single point electrode interface to the skin, a wire will run to a separate box of electronics. So you've really separated the electronics from the skin, and the interface is just at the point contact established by a wire being pressed against the skin. And this is fine, like I said, for hospital use, but if you're going to wear this every day, this gets really clunky and constraining, and the properties of the tape don't match the properties of the skin, so you have difficulty in maintaining robust adhesion. It's constraining the natural motions of the skin, so over time it becomes incredibly irritating. If you want to do more than just a few contacts to the skin, the presence of the wires become prohibitive. So although the integrated circuit technology is racing ahead in terms of sizes of the transistors and numbers of transistors per processor, it's really this interface that's limiting your ability to exploit all that technology in terms of its interface with the body. Okay, so that's what's done. You can get a little bit more sophisticated if you, say, open up that box, you pull the individual silicon chip based circuits out of it, and then you mount those on a piece of tape, and then tape the whole thing to your skin. It's a little more sophisticated. The problem that the tape is not matched to the properties of the skin. I mean, the tape can kind of flex, but it can't stretch in a way that would allow natural integration with the skin. So again, it becomes irritating over time, and it's difficult to obtain robust adhesion in a way that's comfortable at the same time. So the challenges then flow explicitly from either the paste-on electrodes or difficulties in gluing chips to the skin. That is, it's challenging to establish an intimate and highly functional interface that is viable long-term with the kind of electronic and optical and chemical access that you'd like to have. Adhesion, I mentioned, is hard to do that without irritation. In principle, you'd like the mechanics and shape to be matched, but you can't do that when the circuit's on a wafer substrate. And the other challenges are typical of lots of different things. We're trying to drive the cost down and keep the power consumption low, keep the weight and size minimal as well. So we thought about this problem for a while, and thought about it in terms of what is out there already that does integrate with the skin, forgetting about whether it's electronic or not. And we decided that a kid's temporary tattoo was a useful model to kind of think about, because that type of technology laminates onto the skin, It looks great, and by the way, it can accommodate all the natural motions of the skin in such a way that you don't even know that it's there, essentially mechanically invisible, because it's so thin, it's so soft, it doesn't alter the natural motions of the skin, so it's invisible at the level of the integration. So our thought was that if you could create electronics in a form, physical form, that looks like a temporary tattoo, that would be a nice thing to be able to do. And what does that mean in terms of the actual physics of the device? It would need to be ultra thin, so 5 microns, much, much thinner than that 1 millimeter thickness I mentioned to you previously about the silicon wafer. So that's maybe a 20th the diameter of a human hair, kind of in that range. As light as possible in terms of an aerial mass loading, so maybe comparable to or smaller than the epidermis itself, a milligram per centimeter squared is what we thought about. We wanted the stiffness or the sort of the modulus to be as small as possible. So that's a tricky one, but we figured softer the better because it would allow kind of, again, natural motions of the skin without any kind of mechanical loading. It needs to stretch, not just flex, but also stretch because the skin stretches up to about 30%. So those are sort of the mechanics and the weight properties. It also needs to be air and water permeable to allow natural transepidermal water loss. So you need to be able to sweat through this thing. But at the same time, you need the electronics to be waterproofed so you don't get unwanted electrical coupling between the circuits and the skin. And so those are the properties we thought about and wondered, how do you get there? And as a materials scientist, you think immediately about what are the options that you have for the semiconductor material. That's kind of the core building block material for any kind of semiconductor device technology, integrated circuit, sensor, and so on. And you just take a survey of what's out there, and you can kind of separate it into 2 classes. One class of semiconductor material. This is, again, the material that acts as the switching material in a transistor in a circuit. You could separate it in terms of materials that are based on carbon, so organic polymers or small molecule type materials, or you could think about materials that are inorganic, so materials like silicon or compound semiconductors or so on. And you might think about those materials in terms of their electronic performance. And I won't get into the details here. These are different metrics that you can use to assign and assess the performance of these different material options. And you might think the plastics would be a good place to start because you're familiar with polymers and packaging and plastic sheets and so on. And so intuitively you might think, okay, a semiconductor made out of a polymer would be useful to think about in this context. But all known polymer semiconductors are really lousy in terms of their electronic properties. So the mechanics are kind of in the range that you want them to be, but they don't make good electronics. So you can do things like this. This is a team effort that I was involved in when I was back at Bell Laboratories. It was the first kind of flexible ink on paper type display. We used polymer transistors for that. You can do something like that. It's not emitting light. It doesn't switch very quickly. If you want to do a microprocessor, say the guts of a laptop or a cell phone, that's impossible because it's just not fast enough. It can't support that function. So if you want to do something sophisticated integrated with the body, probably the organics are not going to work, or maybe you try to come up with a new class of polymer that would overcome that constraint. Anyway, that's a research topic. Now, silicon is already well developed. You can do this. You can do all these different things. But you normally think about it in terms of that wafer type of format, that platform for integrated circuits. And clearly that's not what you want if you want to wrap something onto the brain. And so you may initially think it would be wise to sort of discard silicon as a material option. And for a while we did, but then we sort of came back to it and ask ourselves, is there any way we could deploy silicon on the body? Because if you could figure out how to do that, then this would definitely be the path of choice. Not only because silicon has good electronic properties, but because there's already a huge established industry around understanding how to use silicon in a very reliable, high-performance way in integrated circuits. So we really came back to silicon and started thinking more about it. And there are a couple of really simple things that and ideas in mechanics that can be brought to bear on silicon to allow it to be deployed in these epidermal formats. And I just want to describe 2 or 3 of those ideas. It really just a very simple level to give you a sense. And the first idea is that any material element has a bending stiffness or resistance to bending that's determined not only by the material itself, but also by the geometry. So if you think about wood, for example, in the form of a 2x4, you can't bend it, but in the form of a sheet of paper, it's very flexible and floppy. Essentially the same material, it's just by virtue of the fact that the paper is really thin compared to the 2x4 that it becomes bendable. Same thing with silicon. So you think about it as a wafer, it in fact does not bend, it cracks almost immediately. It's a millimeter thick. What about if you took silicon and made it, ultra thin, make it 10 nanometers thick, just a few atoms thick? What would it do? Well, it obeys the same laws of mechanics that the wood does, and in particular the bending stiffness depends on the cube power, the third power of the thickness. And so when you go from a wafer, you have something that's very, very stiff to something that's very, very floppy if you make sort of a nano membrane out of the silicon. And so that's a relevant point to think about when you're trying to figure out how to deploy silicon on the skin. The other consequence of thin is that it becomes very bendable because the peak strains in the material associated with bending to a certain curvature go down with thickness. So not only does it become easier to bend, you can bend it more and more as you drive the thickness down. So just like a block of metal compared to a metal foil, the same mechanics, and you can do this with silicon. So you might say, okay, this is great. Let me just replace my wafer with this nano membrane of silicon. I build my circuit here and off I go. That doesn't work because although this thin silicon has these nice mechanical properties, it's extremely fragile. So it cracks really easily. You can fracture it, and the fracture will start on an edge. You really have to think about this membrane of silicon not as a platform for integrated circuits, but just as an active material for building circuits on some other type of substrate that gives you the mechanics that you ultimately want. And so we like sheets of plastic and slabs of rubber, as I'll describe in a second. So you really use this material, you glue it onto these other foreign substrates, and then you use that as a platform for making the circuits. So that's kind of concept number one, and you can implement that in the form of circuits that have properties very similar to the ones that you would ordinarily build on a silicon wafer. But if you do that in this thin geometry for the silicon and you put it on a very thin piece of plastic, you have good electronic properties, but really interesting mechanics as well. So here's an example of a very, very flexible silicon integrated circuit, just like one that you would build on a wafer, but now on a very thin foil of plastic. And so bendable, you can wrap it around the sharp edge of a glass cover slide. So you can bend it to really tight radius of curvature without killing the electronic properties. So you'll still make transistors that switch on and off. You can make integrated circuits. You can make all kinds of devices that you would ordinarily make out of silicon in its usual form. So you might say, great, okay, now I'm in a good position. I can integrate circuits with the skin or the heart or the brain. Turns out you can't because this isn't good enough in terms of mechanics. So if you have a sheet of circuits like this on a piece of plastic, you could wrap something simple like a cylinder or a cone, but you can't wrap a sphere without folds developing. And you certainly can't wrap the brain or the skin or the heart. These are very complex curvilinear contours. So you need something that gives you the ability not only to bend, but also to stretch like a rubber band. That's what biology is all about, not only bending, but stretching. And there's no thickness that you can get silicon to that will allow it to stretch. It just becomes more and more bendable. So you need one more idea added on top of what I just told you in order to get stretchy properties. And it turns out that is very easy to do as well. So step one, create this thin, ultra-flexible silicon. Step two, take it and bond it to a rubber substrate. Now, you probably can realize if you want something stretchy, you need to use a rubber substrate in the first place. But don't just bond it to a rubber substrate. Bond it to a pre-stretched rubber substrate. So stretch it out a little bit, then take the silicon, bond it onto that pre-stretched rubber, then allow the pre-stretch to relax. It snaps back into its original dimensions. And in doing so, it applies a compressive stress on the silicon that creates it to buckle up out of the plane. And it buckles in almost a perfect wavy geometry. So these are little strips of this ultra-thin silicon bonded to a rubber substrate down here after that pre-strain is relaxed. And this is nice because this is now essentially an accordion made out of silicon. And in that accordion geometry, you can now stretch the substrate back and forth. The silicon does not fracture because it can trade out of plane displacements for in-plane deformations. In particular, I can stretch it out. The amplitudes of these wave structures go down. The wavelengths go up in a way that avoids any fracture-inducing strain in the silicon. Likewise, I can compress this substrate, and the silicon responds by increases in the buckled wavy shape and decreases in the wavelength. So back and forth like that, you can achieve effective stretchability in a material like silicon that's intrinsically brittle. Now, that's the basic intuition, and there's no need for present purpose to go any more details. But I just want to point out that the mechanics and the understanding of the fundamental aspects of how this very hard and soft integrated system behaves is crucially important, because you need to understand where the stresses and strains are, how to engineer this system to avoid cracking the silicon. So you have very brittle material in here. You really need to engineer it carefully. So we spent a lot of time understanding the detailed mechanics, and in these kinds of technologies, when you design a system, you design the circuit layout, but then you also have to pay attention to the mechanics. So circuit design and mechanics design go hand in hand. But those are the basic ideas, and I don't need to tell you anything more than that for you to kind of get the gist of how this works. Other than to mention that buckling can be exploited in that very simple layout or in very complex ways where you're exploiting buckling both in the plane and also out of the plane. And that's what we're doing here. To get something into this skin-like form, we not only use strips of silicon, but sort of an interconnected woven mesh of silicon strips that support the circuit functionality. And this mesh is a very open structure. It's bonded to an extremely low modulus, soft silicone membrane support. If you pay attention to the mechanics of this layout, you can construct a circuit like this that if you stretch it, it has a stiffness almost exactly the same as the skin. So you can see these are the response curves associated with a circuit in this kind of layout, and this is how skin responds when you strain it. You have to apply this different stress, and you see all the curves overlapped here. So these kind of ideas allow you to build circuits that have stiffnesses and softness that is very well matched to the surface of the skin itself, and that's kind of one of the goals here. So those are the ideas. What does it look like in terms of the actual device on the skin? This is a picture of one of these sort of filamentary serpentine spiderweb mesh circuits just laminated onto the surface of the skin of the postdoc who did the work. And then we had a glass rod and we sort of poked them right here so you can see how the skin deforms and moves around. And you can see how the circuit just follows the folds of the skin that are induced by that poking motion. Okay, so that's what it looks like. Now, in this case, there are no straps, there are no adhesives, there's no penetrating pins, there's no gel. This thing will just cling to the surface of the skin naturally, just through generalized sort of van der Waals adhesion forces. Same reason why a gecko can climb on the ceiling. These circuits can cling to the skin. It's the same type of physics. And it relies critically on the ability of the circuit to really conform to all the textures of the surface of the skin. I'll come back to that in a second. But it means that these things are not bonded strongly in an absolute sense, so I can grab one on a corner and just peel it off. And if I do that, that's what it looks like. This is a pair of tweezers. We have one of these things, on its edge. And you can see, from this image, what the mechanics are like. It's so thin and soft that it doesn't even support itself. It just collapses on its own weight when it's pulled off of the skin. So very much like the skin in terms of its physical characteristics. So you might be wondering then, if that's what it looks like, how do you even handle it, move it around, and get it on the skin in the first place? And to answer that question, we just went back to the world of kids' temporary tattoos, and we realized that when you manipulate those types of devices, you oftentimes use a water-soluble tape as a sacrificial substrate. We can do the same thing. So we use polyvinyl alcohol. It's a water-soluble polymer sheet. We put our epidermal electronics on top of that. Now we can grab this thing by the edge, no problem, flip it over into contact with the skin, and then just wash away that PVA backing, and that leaves just the epidermal electronics kind of clinging to the surface of the skin using by those van der Waals forces that I mentioned to you. So let me play you a movie, and this will kind of illustrate that mounting process and give you a sense of how this works. So here's a test platform circuit using the ideas that I described to you. It has a bunch of basic building blocks for more complex integrated circuits and sensors. It's an array of transistors and sensors of various types. I'll describe that in a second. What you're looking at here, this is a transparent film. That's that PVA, that water-soluble tape. And the postdoc is just applying a little bit of water with his index finger to the back of that tape to wash it away. So it's gradually washing away. That will leave the integrated circuit, the epidermal electronics, pressed against the skin on one side. And on the other side is this very thin, soft silicone membrane support. So the circuit is sandwiched on both sides by skin and silicone. And that's how it works. So the PVA now is almost completely washed away. And now you'll see how this thing responds. So it's an array of transistors, RF diodes, inductors, capacitors, LC oscillators. There's an array of temperature gauges, strain gauges. There's an inductive coil for delivering power, and there's an antenna running around the outside. I'll describe more details about that in a second. Here's the way it looks when you pinch the skin. You can see how it deforms naturally with the motions of the skin. This sort of bright, shiny region, that corresponds to the boundary of that silicone backing layer, and of course that's where the circuit is. Now note that where the skin is buckling in regions where the circuit is not, looks very similar to the way that it buckles and deforms where the circuit itself is located, suggesting that the circuit is not constraining the motion of the skin, and that's by design. So these things, you can't even feel them when they're on the skin. So you can squeeze it, you can pinch it. There's no adhesive, but as I mentioned before, if you want to peel it off, you can. You can grab it on an edge and just peel it back. And this is what it looks like when you do that. So you're peeling off that backing layer and the circuit along with it. It gets stuck a little bit more there for some reason. You eventually peel it back. It tears off a little bit. But this gives you a sense of what it looks like. I mean, it's very sort of biological at some level, a little disgusting in some ways. Now, it's not adhered very well, but if you want it to stick better, you can just use a tattoo. This is already FDA approved, has a nice adhesive built into it. So we created a custom Illini pirate tattoo for demonstration purpose. And now the circuit is right here. So not only does the tattoo give you more robust bonding, but it also conceals your electronics. If you have a clandestine application in mind, you can hide the electronics behind the tattoo. So that's kind of the way that it works, and it goes on fine like that. So I have some on my arm today, and I'll show you one of these things, and you can come up after the talk if you want to get a sense of what it looks like and what it feels like. I have the conventional wearable device here on my wrist. I have the Illini tattoo here. I have that test structure that you just saw in the movie. It's here. And then I have a slightly more advanced version here on the innermost part of my arm. So these devices are on. They bond quite well. I have a USB-enabled microscope, so you can see what these things look like. So that's my bare skin. It's a little disgusting. I'm not a lizard. This is what your skin looks like too, if you've never seen it under a microscope. But it gives you a sense. It's like really extreme textures here. And so if I go look at the device, you can kind of see it there, quite well bonded. That's the larger scale device. This is one that involves smaller serpentines and just finer patterns of this kind of mesh architecture. It goes on the skin. These things will stay on for about a week and a half or so. I can take a shower, I go swimming with these things on. They're bonded quite well. Oftentimes we'll use this conventional spray-on bandage to kind of seal it up on top and make it even more robust. But these things cling to the skin because they're matched in their properties to the skin. Is one of the key features that I've pointed out a few times. So this is what it looks like under high-resolution microscopy. So this is a polymer replica of human skin, and then on top of that, we've integrated one of these mesh-type circuits. And you can see how that kind of construct allows the device really to conformally follow the curves and the textures of the skin, even down to some pretty extreme folds and crevices. Not completely perfect, but does a pretty good job. And I've mentioned that that's important from the standpoint of adhesion. Let me say a few words about the consequences of the use of these devices to measure body processes through the skin. Because if you want a high information interface, you need it to be conformal like this. So not only good in mechanics, but it's also good in terms of electrical measurements. And there's all kinds of processes in the body that have electrical signatures associated with them, as you probably know. So as the heart beats, it creates time-dependent variations in electrical potential throughout the body. And these devices can pick up that signal when mounted on the chest. And so this is what it looks like. Each spike here is a single beat sequence of the heart. If you zoom in on one of those spikes, you see the full kind of QRS waveform associated with contraction of the various chambers of the heart. And so this waveform can tell you something about cardiovascular health in the same way that those paste-on wires could do that in a clinic. But the idea is this is much more comfortable to wear. So you can imagine, measuring detailed aspects of cardiovascular health continuously all the time. That's one example. The other example is that any contraction of a skeletal muscle also creates a potential, a voltage that you can read out. Here's an example of one of these devices mounted on the leg, and the subject is sort of walking along like this. So you can measure characteristics of gait associated with that kind of waveform, and then the subject stops walking here, and you can see the oscillations in potential stop. So this is this epidermal electronic system. For point of comparison, if you wire up your leg with one of these paste-on electrodes with a wire and a gel, you measure essentially the same thing. So the signal levels, the type of waveforms you measure are almost the same. So we're not saying we have better fidelity in measurement, but this is electronics. This is just an electrode. So you can do many thousands of electrode contacts. You can integrate amplifiers and radios and other things in this format, and you don't need to use a gel. So there's lots of advantages, obviously, to this measurement, but the data that's coming out is very much comparable to what you would get in a more clinically oriented measurement protocol. So that's the heart, skeletal muscles. If you put these things on the forehead, then you can measure brain waves. So you can see alpha rhythms. You can also do Stroop tests and other kinds of types of evaluations that you would typically do with EEG with conventional electrodes, but this is in a tattoo-like format. So, if you're measuring brain waves, you might think this would be a great way to do a brain-machine interface, and we think that's true, but in general, you're more interested in human-machine interface. Whether that's driven by the brain or some other mechanism may not matter in a lot of applications. And the fact that this device is in this tattoo format, you can really think about integrating it on parts of the body where you would not want a piece of tape and a wire dangling off. So for example, you can put these things on the back of the neck, on the forearm, on the finger, on the jaw. You can put it on the throat, and in fact, if you're a student in the group, you get a chance to do all of this if you're interested. So these things go nicely almost anywhere without any discomfort. Now the neck turns out to be sort of interesting because there's a lot of fine motor control associated with speech. So when you talk, you can pick up this electrical activity associated with muscles in the throat. And if you develop a frequency spectrogram, so this is time along this axis and this is frequency of that measured signal, you see different signatures associated with different words. So you say stop or go, or you even subvocally just mouth the words stop and go. You measure these kind of spectrograms, they're different. And so if you work with people in electrical engineering like we did, Todd Coleman, who are experts in signal processing, he can develop software algorithms that would take data like this and like this. You can use learning algorithms to bend this data into different words and establish a vocabulary. So you can do machine control via neck EMG or electrical activity associated with contraction of muscles in the neck. And so you might imagine that as a way to do human-machine interface. Could be particularly valuable for people who suffer from diseases of the trachea or the larynx. You control a prosthetic, you could do other things, create an artificial speech. And so we think that that's that represents a host of interesting opportunities. When we were first doing this, my students were more interested in developing a video game controller based on your neck. So if you want to play a game with your neck, we have the technology to do that. Not sure how many people want to do that, but anyway, a strategy game. I've never played this. Sokoban, I don't know what it is, but you move the cursor up and down, left and right, just by saying up, down, left, or right. Now, this embodiment was a couple years ago, and so we didn't have fast enough data processing algorithms, all being done in software to allow one to play an action video game, but things have gotten much better. We work with folks in the Beckman Institute to develop some of the back-end firmware to do a faster recognition of these patterns. And so we can do more real-time control. So this is just now published. We did this about a year and a half ago. But this is epidermal electronic-based control of this helicopter. So the postdoc back here has devices on both forearms, and he can issue commands to this helicopter by moving his fists in different ways. And so I'll show you how that works. So the command set involves rotating his two fists in kind of a clockwise direction. That corresponds to the command to lift off. Then he tilts them to the left. That corresponds to a command for this craft to rotate clockwise. He'll go back straight up. It'll stop. Clench both fists. That's the command to fly. Rotate the other direction, and it will land. He'll spool it back up. It'll take off again. And then he'll tilt his fist to the right, and it will rotate counterclockwise. He'll stop it, and then clench his fists again. And what he's trying to do is fly the helicopter back and try to get it to land where he started, right there in that box. So now he's over here. He'll issue the command to drop, and he missed. So he needs a little practice, but you get the idea. You can make that better if you want. So those are some things you can do from the standpoint of electrical measurements. You have this great interface window into the body in terms of measuring potential. What else might be interesting to measure? And we were approached by experts in skin physiology at the National Institutes of Health, and they got us interested in temperature. And you might think temperature is not that interesting. You measure 98.6 or 99, you have a little bit of a fever. It turns out, though, if you have the ability to spatially map temperature and measure temperature not just to 98.6, but like 98.635, if you look at that last digit and how it's changing and spatial dependencies of how that temperature is changing, there's tremendous information content. And we got convinced that this was something worth working on by this video that was sent to us by our NIH collaborators, Alex Gorbach. So what it is an infrared thermal camera image of an individual on a treadmill. And the images are processed in such a way that these 4 black dots are held fixed to sort of remove some of the motion artifacts. So this is a very sophisticated IR camera. It's about $250,000. So it has extreme precision on temperature, has good resolution, spatial resolution also. And you'll see what happens when this individual starts walking on the treadmill, starts walking faster, running a little bit, and then cools off. And this is, for us anyway, quite interesting and made us believers in the value of precision skin temperature measurement. So here goes the individual. He's walking. This is his average body temperature as a function of time. He starts speeding up. You see a little bit of variation here, but nothing too dramatic. He'll start walking a little bit faster here, and what you'll see is that the entire body begins to cool. It starts to become gray, a little bit darker. That's because sweat glands are now firing and you're getting evaporative cooling. You see that to a greater extent now. But as time goes on, you see that you not only cool the body, but you develop incredible variations in temperature and texture. And this variation is not associated with droplets of sweat streaming down. That is actually vasculature that's taking heat in the form of blood flows from deep muscle tissue up to the surface of the skin. And that's playing an important role in cooling also. But the point is that if you can put an epidermal patch around here and measure those temperature changes and the spatial variations in that temperature distribution, that could be really valuable as additional data relevant to physiological status and health and wellness. So here's another example, just to give you a sense of what's going on in your body on an everyday basis in terms of subtle variations in temperature. This is another thing that convinced us this was interesting. So this is the thumb, and what you're seeing, these black spots, those spots correspond to the firing of individual sweat glands. So every time one fires, a little tiny bit of sweat comes up, it evaporates away, creates a local cooling spot. So you have a lot of heterogeneity in spatial variations in temperature, time dependence in those variations, and the ability to measure those can be very important. So I told you these devices are mechanically matched to the skin. It turns out you can create them in such a way that doesn't change any of the natural temperature variations in the skin either. They're so thin, they're so light that they're not blocking sweat, for example. And I won't go through all the data that we have to prove that, but just make the statement. So you can create these things. These are now arrays of precision temperature sensors in these epidermal electronic patches. You can see a picture here. This is an IR camera image of them. And then you can measure temperature. So let me show you two examples. So here's temperature as a function of time, measured with this $250,000 IR camera. And then measured with one of the nodes in this sensor array. This is just, it's very low cost, epidermal patch. The first thing that you see is that during this rest period, the individual is just sitting there, you see these variations in temperature, very low frequency variations, so time scales of seconds or more between the peaks, and very slow amplitudes, but those are intrinsic real variations in temperature associated with vasoconstriction and dilation of the blood vessels in the skin. So as they open up, more blood comes to the surface of the skin, you get a peak in temperature, then they contract back down, then the skin temperature goes down, up and down. The amplitude and the frequency is important indicator of cardiovascular health, so you can measure that very clearly. Then what happens at this point in time is the subject is asked to start doing mental division and subtraction. And what happens is, sweat glands start firing because of that mental stress, and you can see the consequence on the skin surface temperature is an overall decrease in temperature. So the precision of the sensor is almost exactly the same as that of this high-end IR camera. And from an accuracy standpoint, it's almost exactly the same. So you can get information relative to cognitive status by measuring temperature. Here's another example. So now we have one device mounted on the left palm, and the individual's at rest. You can see these oscillations again. Then he's asked to do physical stimulus. So you saw the treadmill. You know what to expect. The sweat glands fire, temperature goes down. Then he's at rest again, and the temperature sort of stabilizes out again. So this may not seem surprising until I tell you what this physical stimulus was. So you have the device on the left palm, and the physical stimulus corresponds to rubbing the index and the thumb together on the right hand. That's the physical stimulus. And so because the entire body is a coupled system, a little bit of heat generated on the right hand creates sweat gland firing on the left hand, and you can pick that up in this very subtle change in temperature. So anyway, you can really identify things that you might not think are even measurable by using these kinds of approaches. Okay, so let me, in the interest of time, just kind of skip through here. We have ways to put these things on fabric. We have them use in human clinical trials at the medical school here with Northwestern, and in this case we're using them to monitor wound healing processes, so we can measure spatial distributions of temperature as a function of time as wounds heal. And so that's a first example of a human trial in a hospital setting with these kinds of devices. We also have used them in the driving simulator at our Beckman Institute to measure all kinds of body parameters as an individual is driving a car in the simulator. But maybe I'll spend the rest of my time talking a little bit about how you get this stuff out of the lab into the real world. So we've done driving simulators. We've also done real races. So this is Pauly Haraka. He's a younger driver on the NASCAR circuit, and he has been sort of guinea pig for our devices in monitoring for NASCAR races. So this is one of our devices on his forearm. It's designed to measure skin hydration, temperature and strain, and EMG as he's racing around the track. So to the extent that this is a sporting event, this is a first example of use in sports and fitness. I don't know what the data is good for, but it is a good way to demonstrate the technology because this is a very demanding environment. It's very hot in this cockpit, and they drive around and around and around for very long periods of time. And it's a good way to sort of test the ruggedness and robustness of the devices. So that's one example, sort of real world. It's maybe interesting possibilities in terms of driver monitoring. Maybe in the case of races, but also just everyday driving, it could be interesting to do that. More traditional sports are also of interest. So MC10 is the company that we have in the Cambridge area that's attempting to commercialize this technology, and I'll show you their first product in a second. This is Matt Hasselbeck. So he was a prominent quarterback in the NFL for a number of years. Seattle Seahawks took him to the Super Bowl in 2006, multiple Pro Bowl awardee. This is the device I'm going to tell you about in a second. Here, this is him at the Consumer Electronics Show in January. That's one of our epidermal electronic devices on his throwing arm. So that was a kind of a cool milestone for this technology. But what I'd like to highlight is the device that he's wearing. So this is a soft good, sort of a standard spandex type skull cap. But what's of interest is the electronics that sort of thread into the brim of this skull cap. And what it's configured to do, and I have one of the devices here, is it's a piece of electronics that via this soft good ends up mechanically coupled to the head. And the end of this device has 3 accelerometers and a gyro. And so when impact to the head is suffered in a contact sport like football, these sensors trigger and measure the detailed time profile of accelerations in all 3 directions and rotations. And that information comes down to this base unit, which emerges out of sort of a tail section of this soft good. It's interpreted, and that data is then binned into 3 categories: mild hit, moderate hit, or severe hit, just based on the physics of what's happening to the head when a player suffers an impact. And the idea is it provides a quantitative assessment of the severity of the hit, and that data can then be used by coaches or parents or healthcare professionals to determine an appropriate course of action after a hit is sustained on the field. So we started working on this about 3.5 years ago, long before the issue of concussions became sort of prominent in people's thinking. But I think it does provide a really powerful level of functionality in that context. And because it's coupled to the head and not the helmet, it's measuring the relevant acceleration profiles. The motion of the helmet's not as important. And also because it's decoupled from the helmet, it can be used in multiple different sports, not just football, but hockey and lacrosse are 2 other areas where people are interested in the same kind of thing. So this was launched in July. It's a joint product between Reebok and MC10. And so you can go to this website and you can order this device. And so I encourage you to do that. Order early, order often. We're trying to move product here. So it's a very, very nice piece of technology in my opinion. So MC10 is kind of an interesting technology company because in addition to the usual technical advisory board, we have a sports advisory board. So Matt Hasselbeck is on that, Matt Burke, Grant Hill, a number of other prominent athletes in other sports, and they provide active advice to MC10 around what kind of electronic functionality would be most important in the world of sports and fitness. And sort of leading up the charge from MC10 is Isaiah Kosvinski. He played 8 years in the NFL as a linebacker, and he's been with MC10 for about 2 years now. And so that's fun to be involved with these guys. Andrew Luck just joined the Sports Advisory Board a few weeks back, and so we're very fortunate to have him involved in this development process as well. So those are some applications in sports. I think those are great things to think about in terms of the research that we do at University of Illinois. We're still prominently and primarily focused on healthcare, and let me sort of conclude with this, which is that these paste-on wires for measuring ECG, for example, are a nuisance for an adult. But for an infant, and particularly for premature babies, where you need to do lots of monitoring, this becomes a severe issue and a problem that needs to be solved, in my opinion. And we're hopeful that the kinds of technologies I've told you about would allow a future that looks more kind of like this than what's going on in the present day. So you may be wondering, no, we have not put these things on a baby. This is just Photoshop, but that's what we're thinking about in terms of the future. And I think we have a lot of the pieces that will allow us to do that. So with that, let me just kind of conclude. So the ideas I talked to you about are useful for skin integration. I won't say much about it, but we've done a lot of work on the brain and on the heart using similar ideas. These are more interventional devices used as diagnostics or therapeutics during surgical procedures. But just as with the skin, the ability to put electronics on these soft textured surfaces really opens up new measurement and therapeutic modalities, both in brain surgery and in interventional cardiology, where we can wrap electronics all the way around the outside surface of the heart. And not just electronics, but light sources as well. So the same ideas can be applied many places in the body. So with that, let me just conclude. So we're material scientists. We try to focus on what we're good at. But to do things that are more impactful, we find that it's useful to collaborate. So we work with a lot of talented senior collaborators, different places, Northwestern, Illinois Penn, NYU, UCSD, Washington University on mechanics theory, manufacturing approaches, neurology and neuroscience. Todd Coleman is sort of the EG-BMI guy. We work with Igor Efimov on cardiology topics. But the most important people, really are the students and the postdocs. So they do all the work, come up with a lot of the best ideas. I just get to talk about it. So I want to conclude by thanking all of them for their contributions and their hard work. And thank you for your attention. I'd be happy to answer questions if you have any. Questions? Yeah.
Questions, right?
Yeah, I will. I got one back there. Yeah.
Fascinating stuff, really. So I was wondering, I don't know if you mentioned that, how do you get the signal from the patch?
Yeah. So I'll just start by saying this technology is brand new. So this is not an end point. It's more towards the starting, regime of development of a new technology. So the way that we've been thinking about it is develop as many sensor modalities as we can, even if we might have to use a wire to get the data out. In parallel, develop the radio communication capability, which we ultimately want to have in these devices. So much of the data that I showed during this talk was collected with a thin, stretchable ribbon cable that you can reversibly apply to an edge of the device. You sort of laminate it on, you can pull the data out, you delaminate it, and then you go off about your business. You come back and you want to measure again, you do the same thing again. We have working radios at this point in the lab. I didn't talk a lot about them, but a lot of the devices that I did talk about are sort of building blocks for those radios. So if you can do a high-speed transistor, in principle, you can do a radio. And so we've done that now. So we're now working to put all that together, the sensors with the radio, because that's the ultimate vision that we have here. So that's a good question. The associated question, which you didn't ask, but I'll just answer it and preempt it, is where do you get the power? And that's a good question, too. We've thought about a number of different options. We have devices that allow us to harvest mechanical energy from motion of the body. So these are things that go on the heart, and we can harvest electrical power from the motion of the heart. We can do small-scale solar cells as well. We can do batteries. So we have stretchable batteries. I can show you some movies of those later if you want. It really depends on the power requirements, like how much power you need, which option you ultimately want to choose. But the one that we like best is based on wireless power transfer. So you have a cell phone, for example, it's putting out a fair amount of RF power when you make a call. If you can harvest some fraction of that power into your patch, you can use that to operate a radio on the patch or a sensor on the patch. So we have ways to make antenna structures that go in this kind of format, rectifiers that allow us to take the output of that antenna, convert that oscillating electric field into a DC electric field, and then we can power devices, LEDs and radios and so on. So we like wireless power transfer because the antennas and the rectifiers can be made in this super thin geometry, very much like the devices I showed you during my talk, as opposed to batteries, which don't scale down in the same way that the transistors have been scaling over time. So batteries are a little bit trickier, and that's why we like the wireless approach. Yeah.
How much processing power or memory?
So that's a good question. We like to put the absolute minimum, to keep the cost down and to keep the overall footprint down. The ultimate answer to your question is sort of twofold. One is, what can we do at University of Illinois' academic research labs and the kind of transistors we can build in that context? And the answer is not that much, because the dimensions of the devices that we can build are huge compared to what Intel is doing in terms of state of the art. So if you look at where the industry is going, smaller, faster, cheaper, smaller maps well onto requirements around these device architectures. If you like to be able to include as much computing power in these thin filaments as possible. So as the industry improves, the amount of computing power that we can put on these patches naturally improves as well, because we're using silicon just like they are. So that would be my longer term answers. We'll be able to bootstrap on mainstream development in conventional electronics technology such that we can put enough power on these patches to do sophisticated things. But it's hard to get more specific than that, because it depends on the application and what you're trying to accomplish. Yeah.
Well, one of the big uses of this new technology will be when individuals complain to their physicians, they could monitor them in real time rather than just merely testing.
Yeah.
So
Yeah.
person complains, and then an examination, they
Yeah.
don't seem to be that bad off.
Yeah.
Our brain.
Yep.
Then if you test it in real time, you might get a more
Yep.
accurate.
Yep, that's exactly right. So MC10 is working with large pharma companies where they want to be able to not only sell a customer a drug, but also sell a monitoring patch that allows them to track the response of the patient to the drug itself and determine whether they're taking the drugs on the right schedule or whether that's mismatched. So that's very much aligned with what you're suggesting, sort of continuous health assessment and physiological status monitoring that would be enabled. And so that's exactly where the technology is going. Yeah.
So most of your products are measuring things.
Yeah.
Obviously, you
Yeah.
got a ton of
Yeah.
methods for measuring.
Yeah.
But have you done any work into actually changing physiological things?
Yeah.
Signal, how does it work?
Yeah, that's a very natural next step. So we have a couple of published papers where we're doing that. One involves extremely tiny LEDs mounted onto polymer filaments that are actually injected down into the brain. And there's an emerging area of neuroscience referred to as optogenetics that involves genetic modification of an animal such that specific neural circuits can be either stimulated or inhibited by exposure to light. So in that case, we're using an LED to stimulate release of dopamine, and we're doing sort of neuroscience studies like that. The Bandage project involves an option for heating, so you can locally heat up the wound site. We do things with Medtronics and other biomedical device companies in the context of cardiac therapy. So there we can put electronics on a cardiac balloon, thread it into the endocardial space. We can map electrical activity, but we can also ablate away parts of aberrant tissue using high-frequency pulses of current. So there are lots of things you can do in terms of stimulating optically, electrically, and thermally. Those are the three things that we've looked at. We have ongoing projects that involve microfluidic structures embedded in these same platforms with wirelessly controlled pumps, so we can pump drugs out at well-defined times as well. So stimulate chemically as well. So that's a great question. We have a lot of activities in that direction. Yeah, yeah.
some relationship to that? And also, could you perhaps on that? I think that there are a lot of
Yeah, I mean, right, yeah, so that's a good question. I mean, I think it's natural to, think about the $6 million, cyborgs and, enhanced sensory capabilities by use of implanted devices and so on. I guess you could think about it in those terms, and it's probably worth, some thought. Our focus is much more on things that have value in a clinical healthcare setting, because my own feeling is, if you want to take the skull cap off to treat an acute form of epilepsy, that may make sense. If you want to take the skull cap off to put a device in that will allow you to see it in the dark, maybe not, right? So maybe at some point that kind of the invasiveness needed to get to the devices into the body would be compatible with the benefits that might accrue from having the device there. But I think we're probably pretty far away from being at that stage. But yeah, people ask all the time about cyborgs and how this might, play into that vision of the future, and we just haven't thought deeply in that respect. We're sort of, wound up and completely consumed by trying to do things, advanced surgical tools or monitor stimulating devices, that sort of thing. But yeah. How would we what? Market it? So, I kind of wear two hats. My primary role is at the university, working with those guys, teaching them how to do research, publishing papers, establishing new scientific knowledge. My other hat, which is minor by comparison, is to try to move the best ideas out of the lab, out of the hands of graduate students, into the real world through startups. And MC10 is a good example of that. So we don't spend a lot of time considering marketing. MC10 does that, and they do a great job of it. And so I think this concussion product is a great example of where the ability to flex is important, and the function of the device is addressing a real problem that people care about. And they've been able to partner with with a really great company in terms of Reebok. The other areas that MC10 is thinking about, and this comes directly to your question around marketing, sports and fitness is one. Measuring concussion impacts would be one possibility. Measuring sweat loss would be another, so you don't dehydrate. Temperature, ECG, all these kinds of parameters are useful in that realm of device possibilities. The other one, it turns out to be in cosmetics. So cosmetic companies are very interested in skin, the health of the skin, the properties of the skin. Being able to deliver to the surface of the skin in a completely non-invasive way, high precision instrumentation essentially is what we're providing, is of high interest to people who make cosmetics for a living. So that's another one. The other is more in the realm of clinical health and wellness monitoring. We're talking about that a little bit before. Could be useful for a primary doctor to understand the health patterns of their patients, but also pharma companies trying to understand the impact of drugs on their patients. That's another one. Then sort of at the far extreme of the other part of the continuum are advanced surgical tools. So soft, stretchy tools that interface with the body in a very natural way, allowing high information content measurements and different kinds of therapies, and ultimately long-term implants as well. But from a marketing standpoint, from a commercialization standpoint, they're looking at things that are nearer term, focusing on those as opposed to things that require a very long regulatory approval process. Not that those aren't interesting and valuable things to do, but that's a 10-year type of effort in many cases, or at least 5. So they have some things there, but trying to focus on the near term. Yeah.
So your silicon thickness is not for you to build circuits.
Yeah, that's right. It's yeah. So it's a very relevant point. So it turns out that there's a wafer technology known as silicon on insulator technology, and that type of wafer involves a very thin top layer of silicon sitting on a layer of silicon dioxide, and then the silicon dioxide sitting on the wafer itself. And there are all kinds of design rules and approaches for making high quality devices just out of that thin top silicon layer. And the thickness of that top device silicon in an SOI platform is about the same as what we're using here. It's tethered, though, to the wafer, so it has the bad mechanics. But in terms of feasibility of making circuits, it's already been proven out in that commercial SOI type technology. So if you look at that kind of wafer, if you look at even a conventional wafer, most of the silicon material is not playing an active role in the operation of the devices. So you might ask, why is it there in the first place? The reason why it's there is you need something that's robust enough that robots can sort of move it around through the fab sequence. So that's really what's setting the thickness of the wafer, not anything related to the electronic function of the circuits that reside just on the surface. Yeah.
Following up on the marketing question, maybe from a different angle, I have two questions. One, the intellectual property. What is it that is actually intellectual property? Commercially viable products,
Mhm.
is it the underlying technology itself?
Yeah.
And then the second question has to do
Yeah.
with, and they hold the rights, everything that goes into patents, they the wraparound.
Yeah, yeah.
And then they commercialize at different,
Yeah.
opportunities come up.
Yeah.
And if they are the holder of the rights, how did that occur?
Okay, so your first question has to do with the nature of the IP, and the short answer is all of the above. So it includes basic ideas around the mechanics of how you get hard materials on soft substrates so that it stretches without breaking the hard stuff, mechanics, materials, how do you create this thin silicon in the first place? A lot of, a few filings around that. How do you manufacture these things? How do you move that silicon around without cracking it? How do you build sensors that are measuring relevant things? How do you do that in a precise and robust way? So we have some sensors patents. Most of the IP that we file through my group at Illinois are in that realm. So fundamental concepts in materials, mechanics, manufacturing, and sensors. That's it. University of Illinois owns all of those patents when they're filed. MC10 comes to University of Illinois to get licenses to those patents. The way that we set it up, it was an exclusive field independent broad license to that bucket of IP. It doesn't pertain to any foreground IP, so they don't own me going forward. I can file stuff, as time goes on. MC10 has to come back to the university to get licenses to those things if they feel that it's valuable for their businesses. And from a practical standpoint, it's in everybody's best interest probably have everything end up with MC10, but there's nothing contractually that guarantees that they have access to that because the university has a fiduciary responsibility to the university, not MC10. So MC10 files their own patents, and most of their patents are focused more around what you were referring to, like specific device embodiments. Like Illinois does not own any patents around a concussion, like an impact monitoring device. Like this is not a concussion monitoring device. This is just measuring the physics, not the physiology of what's happening in the brain. MC10 filed those. They identified this as an interesting application. They took the foundational IP, applied it to this particular opportunity, established the relationship with Reebok, did all the manufacturing, everything. So I can't take credit for anything specific around how this is constructed, how it's operating, even this particular application. So MC10 files their own patents. And then they add to that, in terms of their overall portfolio, the exclusive licenses they have out of Illinois. So you may ask, why do you do exclusive? Why do you do field of use independent? It's because when MC10 is launched, they don't know what they're going to do. And the venture capitalists who invest in MC10 want to be sure that they have the flexibility to go after the most compelling opportunities, and those things change over time. So you could imagine slicing the fields up narrowly and doing licenses in that way. It's a viable model, but in this particular case, MC10 was launched before we knew what this stuff was really good for from a commercial standpoint. And then they kind of figured it out. I'm on the board and stuff like that, so I'm involved. But that was the rationale. Did that cover both of your questions? Yeah. Okay. Yeah.
I'll get my own MC10. Who is part of the Allen's question? Who funded the research?
Yeah. Okay. Yeah. So all the usual. Right. All those groups. Yeah. Yeah. They own the patents. The university owns the patents. So it depends on the organization, and I have to go back and look at the details around the contractual aspects of the grants themselves. DARPA, for example, maintains a right to have made. So if you create intellectual property with DARPA funding, they can say you can go off and license that, try to productize it, build companies around it. That's in their best interest too, because they ultimately want access to the technology. But you can't lock it up. If we decide we want products built around that IP, you're not going to do it, then I can go to some third party and have them build the device I need using that IP. That's my understanding of it. I think NIH is somewhat similar. NSF is not quite like that. I'd have to refresh my memory, but there are sort of terms of that sort embedded in some of these grants. Now, if a company had funded the foundational work that we had done here, typically they would own the IP that came out of that funded effort. But in this case, it was mostly, was exclusively government supported, discovery-based research in the early days. Yeah.
These last for about a week. Why do you think that is going on?
Yeah, it's a good question. So, this is lasting more than a week and a half. So just, when we say the epidermal stuff is kind of last, and it doesn't mean that the device necessarily dies. The skin is exfoliating dead cells. So this thing is bonded, it's matched to the skin. Everything that you can control from an engineering standpoint is sort of optimized for adhesion to the skin, but the skin itself is unstable. It's like coming up, right? And the exfoliation time scale is about 2 weeks. So this thing will start getting ragged at about the 1 week point. And you can kind of try to keep it there. You spray a little more spray on bandage, you get it there, but into 2 weeks, it's starting to look ugly. So, number one is, our experience is that there's lots of interesting applications you can address, even with a 1 week kind of residence time. The other thing is you can peel these things off, clean the skin, and then reapply them. And then you reset the clock. And so you can kind of cycle through that way. Yeah. Oh. So it's going well. So. Yeah, so we have that grant jointly with Todd Coleman, who's now at University of California, San Diego. We're device and materials guys. He's plugged into the medical school at UCSD and Scripps. And so our devices have been used for pregnancy monitoring on real pregnant women. So you can put these things on the stomach and you can measure fetal ECG, independent from the mother's ECG. So we have a lot of data like that. A lot of the work around radio frequency communication technology that I was mentioning before has been built out in the specific context of pregnancy monitoring and that Gates grant. So the $100,000 sort of initial period is meant to establish feasibility, and we're right at the tail end of that time frame. And so we're putting together a package of data and a proposal that would allow us to extend that work in a more robust and meaningful way. It was just a point of reference. $100,000 buys you about 2/3 of a postdoc for a year. So you can't do a whole lot. But we do have real data off of pregnant women in a clinical context with these kinds of devices. So We think that's pretty good based on the time frame and the funding amount. And we hope that we will be able to extend the work in a significant way soon. Yeah. Yeah. Yep. Yeah, definitely. So we focus mostly on mechanical energy harvesting, and in that case, the heart, the lungs, and the diaphragm are a natural source. You got continuous motion all the time. If you're doing mechanical energy harvesting on the forearm, it's not going to work out that well for you. So we have devices that have been used in animal trials on large-scale pigs, sheep, and cows, all of which have a heart about the same size as a human at the stage of development that we did the studies. This is all at the Sarver Heart Institute at University of Arizona. So we can get devices onto the heart. They're made out of these piezoelectric materials, so every time they're bent, creates a little pulse of current. We have the current coming out, and then we have a battery that stores it. Because if you think about the nature of the motion of the heart, you're just getting little blips of current. You need to be able to store that so you can generate a continuous power output to operate a device. So we have micro batteries integrated with these harvesters, and then it's sutured onto the outside of the heart, or it sort of wraps around the entire epicardium in that kind of sock or sack-like geometry. The lung is okay, but it's not, the frequency is much lower. Our observation from these animal trials is you don't get nearly as much power out of the lung or the diaphragm compared to the heart. Now, there are other ways to think about harvesting energy from the body. People have thought about thermal gradients. Your skin is a little bit warmer than the surrounding air, and so you can use thermoelectric techniques to develop power from that gradient. You can't get much, though, so we haven't spent a lot of time on that for that reason. The other thing is a little more aggressive, and I think maybe has some promise, is you can build a fuel cell driven by glucose. And you can pull glucose out of the body and charge a battery that way. We don't have expertise in that type of chemistry or that type of technology, but other folks are thinking about it. So there may be some promise for that type of approach as well.
Let's take one more question.
Okay.
One more question.
Any more? Yeah. Yeah. So again, that level of research, we're typically not doing it in my university group because it gets a little bit closer to commercialization. But the MC10 guys have cell phone enabled epidermal patches. Right now, they use the NFC function, so you can't use an iPhone with what they have now. So the Samsung thing, you get it close, you can get some data and power transfer from the phone to back and forth to the device. And they have apps exactly like you're suggesting that allow the user to manipulate the data coming off of the epidermal patch. They also have programs with Motorola Mobility to do things that interface with the phone in interesting ways. So it's a great direction to go. Not happening in my group, but definitely at MC10.